the most important chapters in econometrics, which is nonlinearities in variance, or the very popular GARCH and ARCH models. The importance of this chapter is more than many other chapters, because in terms of predictions or making forecasting, we are very familiar with ARMA and ARIMA models, which are linear models. The problem with those linearity in mean or non-linearity in mean models are that in such models, those models can predict only a linear, can make linear forecasts. So if you have mean information, you'll probably get a straight line or an upward or a downward curve while we are trying to forecast in means. However, nonlinearity in mean is better. Gives us better predictions with machine learning models that we studied earlier, and it has been highly applied in categorical variables. If we are dealing with economic and financial models, which are highly stochastic and highly volatile models are better predicted with nonlinearities in variances or the GARCH models. And hence this chapter is not only very important, but is one of the largest chapters in econometrics in this in the Vance Martin book that we follow. We do not predict a linear step one point at a time from another point at a time from t to t plus 1. Rather, we can forecast a nonlinear step ahead, which is really important and gives us a much better prediction of our stock prices or economic variables. So we will go through this chapter line by line, and we will try to understand each line very carefully. That's why there will be quite a few video logs from this chapter, and we will read through each line putting a lot of energy in each of these pages. So what do we use nonlinear models? First of all, nonlinearity in variance. The key input areas are portfolio construction, risk management, and options pricing whenever we are trying to forecast them. The particular nonlinear variance specification that is investigated is the autoregressive conditional heteroscedasticity class of models introduced by Engel, ARCH models. There are two important approaches to modeling the variance of financial asset returns, which are only briefly touched on. The first is the stochastic volatility model that is introduced by Taylor, which we'll only briefly discuss. That has been discussed in chapter 9 and 12. In chapter 12 we have the simulation model. In chapter 9 we have the in chapter 9, what was chapter 9? Let me just try to remember. Yeah, we didn't go through chapter 9 that well. The second is realized volatility, proposed by Anderson, Boleslav, Diebold, and Labis, which is only explored in the context of the Midas model. And I must mention the realized volatility model is highly important if we're dealing with high frequency data or in high frequency data forecasts or estimations. And this has been this is the exercise 10 of this chapter. Now, we were talking about chapter 9 and chapter 12. I really don't remember. Chapter 9 is quasi-maximum likelihood estimation chapter, and that was slightly important. We missed that chapter. Chapter 12 is yet to touch, which is simulation model, and that is very, very important, I guess. And we will go through chapter 12 sometime later. So let's start with exercise 10. Let's start with this chapter first. And currently we are in chapter 19. Statistical properties of asset returns. So there is a plot of asset returns mentioned. I want you to have a look very carefully. So we have A returns, B squared returns, C autocorrelation function returns, and D autocorrelation function squared returns. It seems the returns are very noisy, and so we'll talk about it. Kind of looks like random noise. Closer inspection of the returns reveals periods when returns hardly change and we see market tranquility, and others where large movements in returns are followed, which are market turbulences by further large changes. So when there is a large movement, even more movement happens later on. Following on, the properties is demonstrated in panel B in the squared returns. So there are large movements, and that follows on to even larger movements, so that are market turbulences. And another property was return hardly is changing, that is tranquility period, which gives a time series plot of the squared returns. Y square, very important. From Y square we have captured very important behavior of the market returns. This clustering of volatility is commonly observed empirical characteristic of financial returns, and it gives rise to autocorrelation in the squared returns. So we see it is giving rise to autocorrelation in the squared returns. Is increasing the autocorrelation in the squared returns is it seems they're not increasing, they're steadily dropping, as demonstrated in panel D. The properties observed in this figure for the returns to the FTSE are commonly observed in the returns of other equity markets, and more generally in other financial markets, that is including currency, future, options and bond markets. And I recall the properties that we have discussed are market turbulence and market tranquility period, and simply squared returns captured that tranquility and turbulence period, and hence squared returns are very important because squares give you the variances. The properties of returns are summarized as follows. So first of all, there is no autocorrelation in returns, that is property 1. So rho, as we know, should be 0. With that in mind, we'll try to explain this property. The autocorrelation in the levels of returns that we demonstrated earlier shows that the predicting the direction of asset returns is not possible. So you cannot predict the direction of the asset returns because they are very volatile. They are very volatile. This suggests the following model to be y equals rho yt minus 1 plus vt, very familiar to you. Rho is the autocorrelation function. V has 0 mean and sigma square variance, in which the restrictions of no autocorrelation requires that rho equals 0, and when rho equals 0, the unconditional mean, and I repeat, very importantly, we need to remember again and again, there is unconditional mean and variance and conditional mean and variance. The unconditional mean and the variance of y are respectively, the unconditional mean becomes y equals vt because this becomes 0. So expected y equals expected value of vt, which is 0. 0 mean and sigma square variance equals 0, and the variance is sigma square. And what is the variance? Is the squared return minus yt minus yt whole square, which is this is the squared return minus this is the mean squared, okay, or yt was the mean, so this is the mean squared. That gives us, because this is 0, mean is 0, we are left with ey square, squared return, which is, for this to be equal to sigma square, yt equals vt. So this is the volatility squared or sigma squared v. That was unconditional mean and variance. The conditional mean at time t is obviously based on the information that is available in the past time, which is t minus 1. So now we replace t with t minus 1, and we have the same equation, unchanged, untouched, yt minus 1 plus vt, and then we break this equation into smaller pieces, and we know that in the past the volatility vt sigma square, we don't have vt for the past, so that's 0, and this is the same as before, which is 0, because the conditional mean depends on previous information of your observation multiplied to rho autocorrelation, changed by autocorrelation, and autocorrelation was 0, so this is 0. You can ask, what about the previous information on vt? We don't have it, otherwise it would change by that, so that is 0. So since rho equals 0, so at time t conditional mean will be 0 based on information on previous data. Autocorrelation in squared returns. Okay, so we have talked about unconditional mean and variance, and we have talked about conditional mean at time t minus 1, and both means is 0 and variance is sigma squared. Autocorrelation in squared returns demonstrated is figure 20.1 that we have just discussed, shows that while predicting the direction of returns is not possible, we can predict the volatility. Beautiful, that's what our objective is, the volatility prediction. This suggests a model of squared returns of the following form. Now y square equals not, it's not rho anymore, it's alpha naught, which is the constant, plus alpha 1 y square minus 1, the lagged value of y squared, the lag of the squared return, that's all. So alpha naught plus alpha 1 plus et is an IID disturbance term, and alpha naught and alpha 1 are parameters as we know. An alternative expression of the unconditional variance that we have just discussed and expressed with sigma square, we can obtain that by an alternative expression can be obtained by using the law of iterated expectation and taking unconditional expectation. So we have expected squared return equals, y in place of y square you put the equation alpha naught alpha 1 y square minus 1 plus et, and alpha naught is constant, so it remains constant, alpha 1, and whatever the we're talking about unconditional variance, right? So remember, we're talking about unconditional variance, and the yt square minus 1, again the expectation remains because we don't know the value of it. It depends on our given data, and e expected value of the IID disturbance term. Now we know that y square the variance from unconditional variance is sigma square, and we know that in the conditional mean is 0, so we can rewrite, so this is sigma square, obviously the variance, the unconditional variance is sigma square, and alpha naught plus alpha 1, unconditional variance alpha 1 sigma square plus et is 0. So we have sigma square is alpha naught plus alpha 1 sigma square, and we can write sigma square equals alpha naught divided by 1 minus alpha 1. Now there is a very strong relationship in the unconditional here in this unconditional variance equation. The unconditional variance now in this way will only be positive if the numerator is greater than 1 and the denominator where alpha 1 is there is less than 1. Okay, so alpha 1 should be less than 1 and the numerator should be greater than 0, not 1. It must be greater than 0. The value of alpha 1 hence will lie in between 0 to 1. Another important implication of this expression is when alpha 1 equals 1, unconditional variance will become undefined. Okay, so it will not be defined anymore when alpha 1 turns to 1. That is something we need to remember. So we have a better expression of the unconditional variance that is expressed in the terms of alpha naught and alpha 1. Alpha naught and alpha 1 from the new equation. Now consider the conditional variance. So we have talked about unconditional variance and conditional mean, conditional mean. Now we want to talk about the conditional variance, which is sigma square equals, first of all, y square, the squared return that depends on its past value minus the mean squared depending on its past value, and that is 0. So we are left with squared return depends on its past value or y square. So that is the conditional variance. So from we can jack that into our equation, and we have sigma square equals condition upon past expectation that is depending on past value, and the equation, the new equation, alpha naught plus alpha 1 y square minus 1 plus et. We break data, take the brackets out. Alpha naught is constant, as we know. Alpha 1 y t minus y square t minus 1 gives us unconditional variance that we have just studied. Sigma square is equal to even something depending on its past information is the same thing. It doesn't change. So we have y square minus 1, and then et, which is the disturbance term in the past observation, that becomes 0. So we are left with alpha naught and alpha 1 y square minus 1. Alpha 1 y square minus 1, that is exactly the same. Y square equals sigma square in the conditional variance, in unconditional variance, and so in conditional variance is just alpha naught plus alpha 1 y square minus 1. That's all. So again, the unconditional variance is just sigma square, and it doesn't depend, it doesn't change even if it depends on its past value. So conditional variance is sigma square equals expected e t minus 1, which is past value expectation, sigma square y square. That is exactly the same as the in unconditional variance, and the value for the conditional variance is alpha naught plus alpha 1 y square minus 1, whereas the value for the conditional this is the value of the conditional variance, whereas the value of unconditional variance is alpha naught divided by 1 minus alpha 1. So this is two things we need to remember up until this stage. Unlike the conditional mean, which is time invariant, obviously conditional mean we have seen doesn't change with time. Unlike the conditional mean, in both cases, as I can recall, conditional mean is 0. Yeah. So it says unlike the conditional mean in 20.2, let's go back, so it's 0, which is time invariant. The conditional variance is not 0. It changes over time as a result of y square minus 1, and that's what we are interested with. The third property, volatility clustering. The volatility clustering property that is demonstrated in the panel D of figure, where we saw autocorrelation function is actually dropping, shows that small movement in returns tends to be followed by small returns in the next period, whereas large movements in returns tend to be followed by even larger returns. This movement imply that the autocorrelation of squared returns is positive, and suggests that in the expression of the conditional variance, volatility clustering requires a tighter restriction. So as I said, the value of alpha 1, because autocorrelation function is positive, value of alpha 1 remains within 0 and 1 for us to be able to capture the volatility clustering property, which is small returns are followed by smaller returns and large returns followed by larger returns. Very important. Conditional normality is property 4. The conditional distribution of returns is normal with the mean that we have talked about, which is 0, and the conditional variance we have also talked about, which is y sigma square and alpha naught plus alpha 1 y square minus 1 is given by y depending on past information is 0 and alpha naught plus alpha 1 y square minus 1. Good, beautiful. For small values of yt minus 1, thus conditional variance is drawn from a relatively compact distribution with mean of 0 and approximate variance alpha naught. Fair enough. This indicates a high probability of drawing another small value of y in the next period. So basically that is hinting us on volatility clustering. By contrast, for larger values of the past information, the conditional variance is drawn from a more dispersed distribution with mean of 0, and variance is not only alpha naught this time, variance is alpha naught plus alpha 1 by t square minus 1. There is therefore a high probability of drawing another large value of yt in the next period, hinting us on volatility clustering. That explains why volatility clustering happens as it happens. And the fifth property is unconditional leptokurtosis. The unconditional distribution is derived by averaging over all t conditional distributions. So when we are talking about distribution as a whole now, we need to take all the conditional distributions and we average them together so that we can get unconditional distribution. Even though conditional distribution is normal, the unconditional distribution is not normal. They are leptokurtic. They are not normal distribution. Each smaller conditional distribution might be normal, but when we average them, they might not be normal. For conditional distributions with relatively low volatility, the normal distributions are relatively compact with high peaks if there is low volatility. Whereas for the relatively high volatility conditional distributions where there are we have higher volatility, the normal distribution, which is average distribution, are more dispersed with low peaks. Obviously, very important information. So if your smaller distributions have low volatility, you will have a steeper peak, whereas compared to when your distributions have your smaller distributions have high volatility, you'll have more dispersed peak. Averaging across the conditional distribution yields a non-normal unconditional distribution, a function of yt, that is the function of yt that has fat tails and sharp peaks compared to normal distributions. So we are talking about averaging, and when we average we have fat tails and sharp peaks. A distribution with these two properties exhibits leptokurtosis. So you see there is a picture, unconditional distribution of FTSE percentage returns compared to conditional distribution. So the conditional distribution, the unconditional distribution, which is averaged, gives us what? Averaging across. So the unconditional distribution, you see the smaller conditional distributions have low volatility. Despite that, when we have averaged, our unconditional distribution gives us a higher peak and fatter tail. Okay, that's what is saying that it exhibits leptokurtic. We have sharp peak and fatter tail when we have average across conditional distributions, and we are comparing the one conditional distribution. This has been averaged across conditional distributions, so we are comparing one conditional distribution with the unconditional distribution of the returns. So when we average across, and very importantly, when we average across, let's forget about the relationship about steeper, more volatile conditionals will give you higher peak and less volatile, will give you dispersed peak well less volatile. The conditionals give you steeper peak for the unconditional. Let's think about when we take average. As a rule of thumb, the peak becomes steeper, the tails become fatter, and that becomes leptokurtic. The distribution, the unconditional distribution, becomes leptokurtic, and that's very important. So here we have used a non-parametric kernel estimator with a rule of thumb bandwidth. Here we have used a non-parametric kernel estimator with a rule of thumb bandwidth. We have studied kernel density before. However, for this chapter, we're just gonna use the kernel function already available in our MATLAB and R that we have used for kernel studies before. And great information. So it has the averaged unconditional distribution exhibits leptokurtic, since it has a sharper peak and fatter tail than the standard normal distribution, and we try to capture that. We are very interested with that. Some very important properties we have discussed, and let's keeping all the 6 properties, or 5. How many? Let's have a look. I think 5 properties. We move forward to the GARCH model. This section discusses GARCH class of model, which captures the autocorrelation properties in the variances. So what's the specification? The specification of the GARCH model is motivated by the discussion earlier, and in particular when we express the conditional variance as a function of lagged squared returns. Fine, if we can recall. So y equals vt, obviously, because nvt is n zero mean and sigma square variance. We have talked about this, and we are talking about sigma square. Now we are talking about conditional variance, which is alpha naught plus alpha 1 yt minus 1. Remember that? Alpha 1 y squared t minus 1. And instead of y squared t, or instead of yt, we have used vt. So here now sigma square t equals alpha naught plus alpha 1 v squared t minus 1. And that is up until I. So I equals 1 to q alpha j v squared t minus I. This model is referred to as the GARCH autoregressive conditional heteroscedasticity Q model, where Q is refers to the order of the lagged squared returns included, is the order of the lagged squared returns. The conditional variance now is Q is the order of the lagged squared returns, and the variance is alpha naught plus alpha 1 vt square minus 1 plus alpha 2 up until alpha q, up until the order vt square minus q, which is equal to alpha naught alpha 1 y square minus 1 plus up until lag q. Here the parameters to be estimated are alpha naught, alpha 1, and for all the lagged parameters, it's a vector of parameters is to be estimated. That is our concern, and that will give us the GARCH estimation. So when alpha equals 0.2, the first parameter in the first column is this. Then, as we can see, as the alpha increases, the news impact curve for alternative parameterization of our Hurn model given in equation 20.9. Okay, let's look into 20.9. A special case of GARCH1 model is when, considering y equals v as sigma square to alpha naught plus alpha 1 v square minus 1 or y square minus 1, they are the same thing actually, with the conditional distribution of y yt, with the conditional distribution of yt is given by the distribution is function of yt that depends on its past value yt minus 1 for all the parameters theta equals 1 by root over twice pi sigma square exponential of minus y square divided by 2 sigma square. We are very familiar with that. We have been dealing with this function for a long time, and in place of sigma square we just put in the rest of the equation on the right hand side, which is alpha naught plus alpha 1 y square minus 1. That's all. Very simple. And this distribution, so with this alternative parameterization, we see as the value of alpha increases, the distribution kind of changes, right, downwards, but it becomes steeper. So this is the news impact curve, but it captures very important information. As the conditional variances increase, the distribution becomes steeper. That also supports our properties that we have just discussed. So the first example is the news impact curve. A property of the Arch1 model is that conditional variance sigma square changes as the disturbance in the previous period changes. We have talked about that. This relationship is presented in figure 20.3, which shows as sigma square increases, the absolute value of so as sigma square increases, the absolute value of Vt minus 1, or the V term increases. This figure also shows that the relationship between sigma square and Vt minus 1 is symmetric, since a positive disturbance has the same effect on sigma square as does a negative disturbance of the same magnitude. So the news impact curve actually proves that there is a symmetric relationship between sigma square and the Vt minus 1 term. Very good. And which is meaning that a positive disturbance will cause the same effect as a negative disturbance on the variance, and that's important to understand. And so they are symmetric. I repeat, this relationship is symmetric because the positive sigma square is affected equally by the by a positive disturbance or a negative disturbance. So beautiful. We have in figure we have shown the relationship between the two variables, intrinsic variables in the equation. So let's see how we can estimate these parameters, because we need to estimate alpha naught, alpha 1, blah blah blah. For each of exposition, the details of this estimation of Arch models are presented for Arch1 specification. The model is estimated by maximum likelihood using a standard iterative algorithm. We have studied that so many times. We use the conditional log likelihood function, then we just pass the function in optimization, as we can remember. So we know the function of yt that depends on its past value theta, and we just jack in 1 by t or on its left. That's all. So we have seen the conditional distribution already for the Arch model. The conditional log likelihood function now will be half log twice pi minus 1 by 2t half log sigma square minus 1 by 2t half log y square divided by sigma square, the very regular, very general log likelihood function. Now what do we need to do? We just need to jack in the right hand side of the equation in place of sigma square. That's all. And when we jack in, we have this new equation. The first now is to find the gradient and the Hessian. The first and the second derivatives. One more time. What does gradient gives us? Gradient gives us the slope, and Hessian gives us a better information, the maximum of where the response variable should be located within the curve. So when the slopes are converging, that is given by the Hessian. The first and the second derivative of the log likelihood function are required because this is optimization. If the parameters are, we are talking about two parameters, alpha naught and alpha 1, are to be estimated by means of a gradient algorithm. Analytical derivatives are easily computed. The first derivative is, you see, d alpha naught So first we're deriving with respect to alpha naught the log likelihood function, and we just include the sigma square terms so that they cross out in a way. So now the log likelihood function becomes being derivated with respect to sigma square and we have 1 by t. We just have to look into this equation. What happens? You take 1 by this is 0, nothing is there. We have a probably you have a minus term on top of it, or to begin with, that remains untouched. We take out 1 by t and we take common in common factor, right? And when we take a common factor, we have log of sigma square, summation of log of sigma square plus y square by sigma square, and in both cases we have 2 in the denominator. So when we take the derivative, we have minus 1 by 2, which remains as it is, minus 1 by 2 sigma square, because log sigma square divided is 1 by sigma square, plus y square to sigma to the power 4, y square divided by 2 sigma to the power 4, 2 remains as it is. And this is just with respect to sigma square, so nxn so with respect to sigma square becomes nxn n, which it becomes just to the power 4. That's all. Yeah, so basically the dx of x square is x to the power 4, and this the right hand side remains unchanged because alpha naught is constant and there's nothing, we don't get anything from this. And so, because as we can see from this equation, there is nothing with alpha naught but 1, so there is no coefficient is being coming except for 1. So now we take 1 by 2 sigma square out, and we have y square divided by sigma square minus 1. That's it, rewritten. So this is all we need to know. We don't need to look into the derivative calculus or differentiation calculus to that extent. So 1 by 2 sigma square, y square divided by sigma square minus 1. Now when we do this differentiation with respect to alpha 1 just in this manner, this time alpha 1 has y square minus 1, so to your right we have y square minus 1, to your left we have the same derivative. We have already derived that, this equation. So the gradient vector now becomes y square divided by sigma square minus 1, everything else remains same. And for the first one it is 1 against alpha naught for the first parameter. For the second parameter is y square minus 1. Beautiful. Now we roll on to the second derivatives. First we derive again against with respect to alpha naught, then alpha naught alpha 1, then alpha 1. So we see with respect to alpha naught we don't have anything. With respect to alpha naught alpha 1 we have y square minus 1. With respect to alpha 1 we have y to the power 4 minus 1, and the terms are the same, 1 by 2 sigma to the power 4 minus y square divided by sigma to the power 6. 1 by 2 sigma to the power 4 minus, because we have this, you see already, you have this, and when you square it again it will increase. When you differentiate it again, the powers will increase by squares. So sigma square becomes sigma 4 becomes sigma 6 to the power 6, sigma square as it is, y square as it is. So very simple. And now our gradient has 4 information from the gradient vector. We have y 1 first for alpha, first we have 1, then we have y square minus 1 non-diagonally, and we have y square minus 4 diagonally 1 and y square minus 4. Everything else remains same. This gives you the Hessian matrix, which is d theta multiplied to with respect to theta transpose, the decomposition. Now this is an important relationship to remember: sigma 4 minus y square divided by sigma 6, because y square can become sigma square anytime they're the same, and then you have a reduction. Beginning with some starting value of parameter, say theta naught, the Newton-Raphson algorithm can be used to update the parameter values using the iterative scheme. So theta equals past value of theta k minus 1 minus gradient divided by Hessian, where the gradient using equation 20.13 and Hessian using equation 20.14, we just talked about the equations, and sigma square is evaluated at theta. The scoring algorithm can also be used in deriving the information matrix, right? However, it is convenient to modify the algorithm by using the conditional expectation instead of usual unconditional expectation. So the conditional expectation is sigma square equals y square. That is the unconditional variance, as we know very well, and win information matrix is simply negative Hessian. So we already had. Did we have any negative value with our Hessian? Probably not. But because we are dealing with negative Hessian, negative term is not coming in. We are not doing anything, which means we might had negative value somewhere in Hessian. No, we never had negative value. This is not coming in because this is adjusted in the iterative scheme. So now in place of y square we have the conditional expectation of y square, which is sigma square, the thing I was just talking to you about. So you cross sigma square out, you have 2 sigma to the power 4 on the numerator denominator. So what do you have? 1 minus, so you have 2 sigma 4, and you have 2 sigma 4. So for first one there's nothing, minus 1 minus 2. Oh, see, this is a mistake. There must be a minus. I told you there is a minus here. Yeah, so there is a minus. So what happens here is sigma 4. So you have 1 minus 2. That's all. Very simple. And 1 minus 2 gives you minus 1. Minus 1 crosses out. So you have only 1 on the numerator. So that is what it is left with that. We have simplified the equation slightly with the information matrix. And this is how the information matrix looks like. It's again the Hessian, just the second term is vanished, and also the sign changes here. In the iterative algorithm, the minus become plus, whereas before, so this is it. Very simple. The maximization of log likelihood function in equations require a starting value. Now, in order to maximize the log likelihood function that we have just discussed, we need to have a starting value, as we know all the time. So the equation was sigma square is alpha naught plus alpha 1 y naught square, y square naught, because we need a starting value of y naught. The simplest solution is to choose sigma square as the sample variance of yt, and which represents an estimate of the unconditional variance of yt. So we might find a regular unconditional variance of yt from our sample, and we use that for optimization, or we can simply put y naught to be 0, and we can begin our optimization from there. So you can take the whole data, you can find a sample variance, you can put that in as y naught, or you can put 0 in place of that. A potential problem in estimating the parameters of the GARCH model is that specification of the variance in equation does not necessarily ensure that sigma square is always non-negative. So we're talking about 20.9, right? We're talking about the regular alpha naught plus alpha 1 y square minus 1. So A potential problem is that in ARCH model specification is that the variance which is sigma square equals alpha naught plus alpha 1 y square minus 1 cannot be ensured that sigma square is always non-negative. Sometimes you'll have negative, sometimes you'll have positive, because your information is based on past information y square minus 1. For example, a negative estimate of a conditional variance may arise in case of alpha naught or alpha 1 become negative during the iteration. If this happens even for just one observation, the optimization will break down because log sigma square cannot be computed. Indeed, very simple. One possible solution is to follow the suggestion made in earlier chapter and transform alpha naught and alpha 1 using an appropriate mapping. Another a popular choice is exponential tilting. Okay, very important. And it's exponential tilting, in which algorithm estimates the transformed parameter. The algorithm is given a transform parameter, which now we have delta I. So instead of finding alpha 1 or alpha 0, we find exponential of delta I in place of alpha I. That's all, very simple. So we transform alpha I equals exponential of delta I. So alpha naught becomes exponential of delta naught, alpha 1 becomes exponential of alpha 1, so that we can avoid the negativity, the arrival of any negative information. Standard errors of alpha I can be computed by the delta method, or the model can be iterated one more time with exponential of alpha delta I replaced by alpha I. So we can also remove this exponential term later on. From the invariance property of maximum likelihood estimators, the estimates of alpha I obtained using this strategy are also the maximum likelihood estimates. So they are valid. Even if we transform alpha naught and alpha I, we can get back to our alpha I by just iterating an extra time, and they give you the exact maximum likelihood estimate. It is usual to confine attention to cases in which the process generating the disturbances is variance stationary. That is, so variance, in cases we like to think that the variance is stationary, that is unconditional variance is unchanging, is not changing over time. This requires alpha 1, as we have said, alpha naught to be greater than 0, and this requires alpha 1 to be less than 1 or within 0 to 1. If your alpha 1 in the equation of unconditional variance, which is alpha naught divided by 1 minus alpha 1, if your alpha 1 is within 0 to 1, then is variance stationary. Estimating an ARCH model. So we have considered percentage returns Y on FTSE from 5 January to December. We have 4,952 observation. The maximum likelihood estimates of the parameters are ARCH1 model applied to the data. Y equals V, and sigma square is alpha naught plus alpha 1 V square minus 1. We know these equations, we just jack in the data, estimated parameters of alpha naught and alpha 1. And from there we find unconditional variance, which is 0.993. You see, this is within 0 to 1, so this is variance stationary. And what we are trying to say is that the sample variance, if you just directly calculate, which is 98%, your unconditional variance is 99%, which is proof that they are consistent. So let's test. A test of ARCH is given by testing the alpha 1 equals 0, so that the model under the null hypothesis reduces to a normal distribution with 0 mean and constant variance. So ARCH is very simply, if your alpha 1 is 0, then you have a null hypothesis reduces to 0 mean and constant variance, sigma square is equal to alpha naught. The null and alternative are, if alpha 1 equals to 0, there is no ARCH. Alpha 1 is not equal to 0, there is ARCH, obviously, because you have y square minus 1. The second term actually we are talking about. And we are left with your conditional variance equals to alpha naught. Let the parameters of the restricted model under the null hypothesis be. Under restricted we don't have any alpha 1, so parameter is just one, alpha naught, where alpha naught is the maximum likelihood estimated of alpha naught under the null hypothesis. For the model in this equation of the maximum likelihood estimator of alpha naught, in that case, you know, the MLE we have 1 by t and y square. Very simple. Just this left, alpha naught equals 1 by t summation of y square. The test of GARCH can be performed by using either LR Wald or LM test. In practice, LM test is commonly used since it simply involves estimating an OLS and performing a goodness of fit test. Information matrix in this case is based on test statistics. So T, you have gradient, transpose and gradient. In between you have the information matrix inverse. So this is just the decomposition, where gradient and information matrix, a gradient vector and information matrix respectively evaluated at the parameter estimates under null. So we know these terms, what gradient are, you know, because we don't have alpha 1, we are not gonna talk about alpha 1, we're just gonna talk about alpha naught, and the gradient is y square minus alpha naught minus 1 for 2 parameters. And for information matrix, you see diagonal and non-diagonal, and remains the same. Using this expression, our LM is ET. ET is, you know, residual, which equals y square divided by alpha naught minus 1, that term, that particular term, which is y square minus alpha naught divided by alpha naught minus 1, which we have seen many times, y square from gradient actually, y square. So this is the gradient term. So ET y square minus 1. So to reduce difficulty, we are just simply taking gradient for these 2 vectors, right? And then we have information matrix, and then we have gradient again, ET y square minus 1. So this, we take this term as ET, and that makes things much easier for us. Alternatively, since under the null z equals y by root over alpha naught, it follows E in the equation has the properties. So this ET gives us further information in terms of generalization or normalization when z equals y divided by root of alpha naught with 0 mean and 1 standard deviation, which is the generalization approach actually, or standardization approach. The property is 1 by t summation of E square is z square minus 1 whole square, or the property is 2, which means the limit of z square is 1 and z to the power 4 is 3 from the properties of normal distribution. The limit of z square equals 1 and z to the power 4 will be 3 from the properties of normal distribution. Consequently, this is the property of asymptoticity or asymptoticity property. Consequently, another asymptotic form for the LM test in equation 20.20. Okay. Another where were we? I'm sorry. Another asymptotic form for the LM test in equation is to replace the half with t by so we are replacing the half with the whole thing, t divided by e square. Okay, so we can replace, if we replace alternatively the half with t by e square, what happens? This is another form which is the inverse of the variance of e. This yields the test statistics LM. So t by, instead of half t by, you know, e square, gives you the same thing, LM statistics. This is just another form representation, another form of representation. This form of LM test may be computed as TR square, where R square is the coefficient of determination from regressing these E on Y and y square minus 1. Beautiful, right? We learned something. R square is, we have studied this before. R square is the coefficient of determination when we regress E on y and y square minus, because under the null E is simply 0. The absolute value of E is 0. An even simpler form is to replace E in equation by y square. Alright, so now let's replace E with y square, since R square is invariant to linear transformation. So with linear transformation there is no problem in R square, it is invariant. So E square equals y square minus sigma square, y square minus alpha naught minus 1. So instead of y square E, you can take this one here, this one here. So you can just do a little bit of transformation. And first we were talking about E was regressed on y or y square. Now we are talking about y square is regressed on 1 and y square minus 1. So first we were talking about E becoming regressed on 1 and y square minus 1. Now we are talking about y square becoming regressing on 1 and y square minus 1. And we compute R square from this regression. This form of R test corresponds to regression equation initially proposed as a model of squared returns. In the very beginning we talked about that. Under the null, ln is distributed as chi-square. So generalizing the LM test to the RQ model is straightforward. The null and alternative are now alpha 1s are 0, no R's or R's. And the RQ is implemented using the following steps. First step is estimate the regression equation by least square, where E is the IID disturbance term. We are familiar with this. In the very beginning we introduced this equation. Then we compute TR square from the regression. So we estimated this regression equation, then we are computing TR square. How are we computing TR square? By regressing y square on 1 and y square minus 1, and computing the corresponding p-value using chi-square distribution. If a p-value is less than 0.05, this is the evidence of R in y at 5% level. That means there is R. So let's test for R. Daily percentage returns of FTSE 100 Dow Jones Industrial Index and Nikkei indexes are there. We tested R with 0 mean by subtracting. So basically there is nothing written, there's just the information given, a math problem, we can do it. So alpha naught, alpha 1, alpha 2, R1 on R2, R square. If we have to look into this information, if the p-value is less than 0.05, so I have to look for less than 0.05. R square, these are the coefficient of regression. We need R square to find TR square, and all of them are less than 0.05, so there is R in every of the indexes we have taken. R in all three equity returns. Beautiful. Then we are going to talk about univariate extension, but at this stage we're going to take a small break, and we're going to stop here, move on to your next blog when we are talking about univariate model. So what have we learned? We have learned how we can represent a squared the squared return in information like stock indexes. We have talked about conditional, unconditional mean variance, conditional mean variance, their values, and what is the relationship between conditional and unconditional variance, and how averaging across the conditionals give you unconditional but gives us steeper value, which is important. We talked about the 5 properties, very important 5 properties, and that how they are proved, how they are related to each other. We talked about ARCH model. From there on we talked about ARCH model and how we can develop the ARCH model. ARCH1 with the help of ARCH1 model, we talked about estimation with log likelihood function, the gradient Hessian information matrix. Then we talked about testing of ARCH and GARCH model. Yeah, we haven't talked about GARCH yet, we're talking about ARCH. So up until this, and then we are gonna start our next extension. Thank you.